In this example, we're examining the limit as x goes to 1 from the right of x minus 3 over the square root of x squared minus 5x plus 4. So the first thing to do in evaluating any limit like this is to begin by just plugging in whatever you're approaching. Plug it in for x and see if it just works out. Maybe it will. So we have 1 minus 3, so that's negative 2 up top. And then down below we have, 1 minus 5 plus 4. So all this is 0 down below. So negative 2 over 0, we know something's going to happen. Often in infinity or negative infinity, but it could be it does not exist. Let's take a closer look here and see what happens. Since we have a radical in the denominator here, we have some domain concerns. Namely, I'm wondering if approaching 1 from the right is even in the domain of this function. So let's just check on that to make sure that we're within the domain, and then we can figure out what it goes to. In considering the domain for this function, we need this whole expression inside the radical to be greater than 0. And it's not greater than or equal to 0 because equal 0 would still have us dividing by 0. So it's strictly greater than 0. So let's just take a look at that, and we have to remember our nonlinear inequalities from algebra a little bit here. So we need x squared minus 5x minus 4 greater than 0. So remember how we do these. You have to factor it down and then do test points in the regions is at least the most complete way of doing it. You could possibly use shortcuts here and there, but I'll go for the full approach here. So I factor it down. We have x minus 4, x minus 1. So that tells us we have x equals 4 for one of our regions, and x equals 1 for the other one. So kind of make a little sign chart here. Let's see what's happening. So 0, and then we have one region defined by 1, and then again at 4. Remember this from algebra, then you do your test points. You pick a test point from each region. So I'll do x equals 0 for this region, that's convenient, x equals 2, and x equals 5. Those are some nice test points, so let's test them. So then we go over here and we do our test. All right, we're just getting an idea of the domain, x minus 4, x minus 1. Right, this was always one of people's, usually they're kind of their least favorite section in pre-calculus or algebra. So let's test a point here. So we have x equals 0. Right, when we plug it in, we have 0 minus 4 is negative, 0 minus 1 is negative. Negative times a negative is a positive. So this whole region here is positive. Then we test x equals 2 for our second test point. Plug it in, we have 2 minus 4 is still negative, but then 2 minus 1 is positive. Negative times positive is negative. So this whole region is negative. And then x equals 5. Plug it in, 5 minus 4 positive, 5 minus 1 also positive, positive times positive, clearly positive, so this whole region is positive. Okay, so what that tells us is this thing is greater than 0. Well, it really gives us the domain because the function is only defined where this thing is greater than 0. So we have the domain then is, well, it looks like negative infinity up to 1, union 4 off to infinity. Okay, all of that to figure out what happens as x goes to 1 from the right. Well, the domain, as we approach 1 from the right, we're coming in here from the right, we are technically outside of the domain of this function if we're really close to 1 from the right. See, we're in this union area, which is not in the domain of the function. Say if we choose like 1.0001, something really close to 1, but we're coming in from the positive direction, which is what this plus means. We're coming in from the positive direction, which is from the right. So anything close to 1, but just to the right of 1, is not in the domain of this function. So what can we say about the limit as we approach 1 from the right when the function is not even defined when we approach 1 from the right, at least close to 1? Well, there's only one thing we can do here, does not exist, which we abbreviate as DNE.